Hello, my name is Antonio Ivanov, and it is my pleasure to welcome you to this presentation on the paper Energy Detectors Performance Evaluation for Interweave Cognitive Radio Network Scenario in 5G, with ID 28 as a part of the International Scientific Conference of Communications, Information, Electronic and Energy Systems, CIEES 2020. This slide shows the presentation's agenda. It begins with an introduction of the core issues which motivate this research work, then explains the developed systems model, details the simulation characteristics, illustrates the obtained results, and finishes with the conclusions. The recent advances in resource allocation methods for 5G heterogeneous networks and dynamic spectrum access, the convergence between them becomes a more prevalent topic in scientific research. Numerous initiatives have proven the underutilization of the spectrum below 6 GHz. In addition, integrating the novel 5G technologies with current wireless standards will be more flexible through the application of cognitive radio or CR capabilities in communications devices. This field is further expanded through the application scenarios of heterogeneous, ultra-dense, and Internet of Things or IoT networks within the scope of 5G. Significant technological advances achieved in the interweave CR networks, which are able to operate on the incumbent or primary network spectrum and independently from the primary network. That is made possible through the vital function of spectrum sensing, which is required to provide accurate assessment of spectrum occupancy by the primary users or PUs so as to avoid unwanted interference in their communications. If the primary user's presence is not properly detected, i.e. a misdetection, the CR network will utilize the spectrum and thus create unwanted interference. Energy detection has been established as the most prominent sensing method due to its speed, which allows for the decision on spectrum vacancy to be made such that the available frequency channel can be used before the incumbent users resume its utilization. This paper evaluates the detection accuracy of two popular types of energy detectors for spectrum sensing within a 5G heterogeneous network scenario through the use of the novel 5G air simulator developed by Telematics Lab of the Polytechnical University of Bari, Italy, which is written in C++ and available on GitHub. The effect of different data stream types and number of primary and secondary users on detection performance is studied via the simulation results. And the system model incorporates a microcell or MC with radius of 350 meters within the scope of which operate the primary or microcell UEs, also called MUEs, and the secondary users also called SUs. All of which are stationary. The SUs are based on the femtocell UEs implemented in the simulator and are randomly distributed within two single-floor buildings with random locations inside a microcell's coverage. The CR spectrum sensing function is implemented within the SUs to determine whether the frequency channel is free from MC and MUEs transmissions or not. Within the simulator, environment score functionality for idle periods for the MCPU is implemented in order to simulate the PU's absence from the spectrum at random times during the simulation. The MC continuously transmits data streams throughout the simulation's runtime. Two common types of energy detection methods are implemented. Traditional energy detection or TED and Rayleigh fading ED or RFED. Detection performance is assessed on the basis of the signal to noise ratio and the detector's performance is characterized using the probabilities of detection and of false alarm. The simulation is performed for two cases of the number of SUs, and for each of them, the detector's performance is evaluated for four different types of data streams: video, voice over Internet Protocol or VoIP, constant bitrate data transfer or CBR, and a combination of those three um, with the title O types for the cases of 5 and 10 MUEs. These are the simulation parameters. For the case of 5 MUEs being present, it is obvious that for both detection types, the results curves follow similar patterns, with the general difference that TED shows slightly higher overall performance. Lowest detection accuracy is exhibited for the CBR traffic, whereas the highest is noted for the VoIP type. This can be attributed to the traffic pattern of CBR, which, due to its non-real-time requirements for communication, leads to more retransmissions in the examined low SNR scenario. And video traffic, just like the VoIP type, has more stringent latency and respectively tolerating loss requirements, and thus less retransmissions and higher detection probability. For the probability of false alarm of the TED, the results show similar patterns but in the opposite direction. It is also observed that there are some discrepancies in the results for the VoIP traffic, which lead to sudden degradations in the probabilities of detection and a false alarm. They can be attributed to multiple retransmissions within shorter reception time and smaller number of samples, and thus lower performance for the same SNR values. For the case of all types, the video stream being the most bandwidth intensive takes precedence over the others, and for this reason its detection accuracy is nearly the same as that of the video stream type. Thus, the curves for these two types, all types and video, is nearly overlap almost completely, and they have about 1 decibel difference in comparison to the results for the VoIP and CPR. In regards to and RFED, the results are very similar, those showing slightly lower performance for SNR levels above minus 10 dB. There is a bigger gap between the results for 5 and 10 MUEs of about 3 to 4 decibel. Also, for more interfering MUEs, the difference between the result curves for the different traffic types is bigger. Thus, the RFED improves the detection performance for the different traffic types slightly more than the TED for the lower SNR ranges, or below minus 10 dB, but the TED still has better probability of detection at higher SNR, but it has variations in its probability of false alarm, whereas the same is always zero for the RFED. This advantage is due to the RFED accounting for fading in its formulation. The result patterns for for 10 SUs follow very similar distributions to those of the alternative. A significant change, however, is exhibited in the results for 5 MUEs, in that they are very close to those for 10 MUEs, and also performance degradations are also notable for the VoIP traffic type. The reason for this development is the interference created by the additional SUs at the and for their uplink overhead communications. It is also observed that nearly perfect performance is reached for lower SNR of uh, um, minus 8 dB, whereas the same is achieved at minus 2 dB in the alternative case. For the RFED, nearly perfect accuracy is achieved at minus 5 dB of SNR. As seen from the results, increasing the number of SUs leads to higher detection performance for both the TED and RFED. However, the increased interference levels as the consequence will deteriorate the SU's communication exchange. And this paper performs a simulation study for two popular types of energy detectors for of spectrum sensing within a 5G heterogeneous network scenario through the use of the 5G air simulator. The simulation results showed the effect of different data stream types and number of primary and secondary users on detection performance. Primary user detection is more potent for real-time data streams such as VoIP or video, which are prevalent in modern mobile communications. Increasing the number of SUs in the interweave TR network has much greater effect on uh, detection accuracy degradation for low SNR levels than the differing number of MUEs. Thus, adaptive interference cancellation is necessary for communications in dense and IoT networks for 5G. With this, I conclude my presentation. Thank you for your kind attention.